All right, hello everybody. Hope you're doing well. Let's look at a problem from a few weeks ago, the permanent income problem. We're going to solve it two ways. We're going to solve it three ways. Once with no randomness, once with randomness, and then once in the context of an open economy model. So we'll begin from the beginning. And these general setup will stay with us as we proceed to more and more complex models. Of course, some things will change. The y won't be known once we're random, but fine. The consumer is going to be a finitely lived consumer, living t periods, and has an exogenous but known income stream, yt, in y0, y1, y2, y3. Okay, think of this maybe as like a bond. The household begins its life with some kind of endowment, and then the endowment is like a financial instrument that's paying a fixed income every period, and we know what that fixed income is when we begin our lives. And the choice is, over the course of our life, how to spend this money. We have two choices. We can either consume it or save it. Why should we consume something? Well, it's going to give us utility today. Okay, we're not going to think about, there's no necessity to consume. By that I mean, there's nothing in the model that says you have to consume to live. Yeah, zero. Theoretically, zero is a allowable choice. Of course, we'll have a utility function that satisfies the analytic conditions, which will rule out zero. But there's nothing in the model in principle that says you have to consume. You just consume because it makes you happy. And then why save? Well, because if you save, you'll get income tomorrow. Yeah, you can transform income today into more income tomorrow. Of course, the price of that is that you have to wait for it. So putting all of this together, we arrive at this budget constraint here. So this is really just follows logically. This just follows from the setup. How can we spend our money? We can either consume or we can save, and these are going to be our expenses. And what is our money that we get? Well, we have our bond, or whatever you want to conceive this as. We have our instrument that provides us YT, and then we have the money that we saved from last period. Okay, so we have end of period accounting here. ST minus 1 is what we chose last period. We got interest on it at the rate RT minus 1. So we knew last period we sort of like locked into an interest rate in the previous period. The next period comes, we get the agreed interest rate on our savings that we had last period. And that total is what we have to spend. And then our problem is going to be to choose CT and ST to maximize the flow of lifetime utility. So we're going to have to solve this every single period. When I say choose CT and ST, I mean in period 0 we have to choose C0 and S0. In period 1 we have to choose C1, S1. In period 2, C2, S2, and so on and so on. What we recognize though, what we know now, having studied the RBC model and spent more time with these dynamic models, is that our choice is time independent. There's nothing special about t equals 1. There's nothing special about t equals 5, t equals 10. We will have the same decision rule, the same decision function, right? This function that I always call g, right? That takes us from xt to xt minus 1. We have g of xt minus 1 given theta and maybe epsilon t. Yeah. This g is time independent. So we find g, it allows us to make the best decision to go from time t minus 1 to time t, and then it's valid for all times. So we don't have to think about choosing C1, C2, C3. We can just think about choosing an anonymous CT and then apply that logic to every single period. Speaking of anonymous, we have an anonymous utility function. Okay, I'm not going to tell you if this is log utility, if this is CRRA utility, if this is whatever, right? Quadratic utility. I'm just going to say it's a utility function. Of course, it still has to satisfy the neoclassical assumptions, and you know what those are. Plus, it satisfies the analytic conditions, which just rules out choices of consumption of 0 and infinity. Okay, so how does this look? I'm going to erase all of this. Maybe before I erase this, given all of this setup now, you could write the household's problem. Yeah. That's a nice exercise. Please have a try by yourself. And then come back when you're ready. Okay, you're back. Let's write the household problem and solve it together. We said that the household's problem is to maximize the lifetime flow of utility, which is defined as the sum from t equals 0 to capital T, utility of consumption. This is subject to a budget constraint. What's the budget constraint? It's exactly as we wrote it. Expenses are equal to what we saved last period plus our interest plus whatever our exogenous income is this period. This definition isn't finished. We have to specify our control variables. We're going to maximize this by choosing CT and ST. Okay. Previously, we had seen how did we solve this when we had two periods. We plugged in, we took this budget constraint, yeah, and we simplified it. We kind of plugged things into each other to eliminate S, the S right before, the S2. We said, okay, well, the sun's going to explode. I don't need to save anything in S2, so we're just going to choose C1, C2, and S1, and then we solved for all of those. Okay, now we have many more periods. In principle, you could do the same thing. You could write all this out, and you could reverse, you could substitute and substitute and substitute. But now we know how to handle these sorts of dynamic setups. We can just do a dynamic Lagrangian. And I made a mistake here, I apologize. There should be a beta, of course. T equals 0 to capital T, and we should discount by beta t. And we're standing in time 0. Again, we have this loosey-goosey notation with the t's. We're standing in time 0, and we're thinking forward. But we're going to solve for an anonymous s, an anonymous t. So it's kind of like two things at once. Okay, so what can we do? We can write a Lagrangian just like this. We don't have to do any reverse substitution. We just do like we do in the RBC model, yeah? We take the Lagrangian, we say, okay, the Lagrangian will be the infinite sum, the finite sum from t equals 0 to capital T, beta t. We're doing a discounted Lagrangian, so we'll move the beta t to the outside. Utility of CT minus lambda t, and then we write the budget constraint. So we're just doing a constrained optimization, like normal. Minus yt. I have no expectations anywhere because this is a deterministic problem. We know the sequence of payouts that result from yt. The only place we could have randomness in this model is this yt. Yeah, I guess maybe rt could be random. Okay, fine. Granted. But the CTs, we choose the CTs, we choose the STs, okay? We should specify, of course, that S minus 1 and R minus 1 are given. Okay, so these are not random. We don't have any randomness there. So the only place really randomness can enter this model is yt, and we said that yt is known. So we don't have to worry about expectations. We just have this Lagrangian. And we're going to maximize the Lagrangian with respect to CT and ST. Okay, understanding that t here is like an anonymous time. Okay, so you know how to do that, right? CT should be like you do with your eyes closed. We take the partial derivative of L with respect to CT, set it equal to 0. Okay, pause the video and have a try. You're back. Okay, so you went in here. Maybe the only tricky thing is working with this anonymous function, but it's not so bad. We're just going to say u prime of CT. Where else do we have a CT? We have a CT here. So I'll do minus lambda t. Lambda t times CT is just, the derivative of that is just lambda t. And that's it. We're done. Great. Change my color. And then we can take the derivative of L with respect to ST and set that equal to 0. Okay. In the first time step, we have an ST here. So we'll have minus plus. So we're going to have minus lambda t, and then the st goes away in the derivative. But we also have an st minus 1 here. So we have to recognize that we need to do the rollout. We need to step time forward and think about what comes next. So we'll have plus, because this is a sum, beta from out front. Now we'll have minus lambda t plus 1 times minus 1 plus rt st. So we'll have minus times minus is plus lambda t plus 1. The derivative of the whole thing with respect to st, the st will go away. So we'll be left with 1 plus rt. We set that equal to 0. Okay, maybe that isn't so clear for you. You should write out the Lagrangian for 2 time steps. Okay, so the t equals 0 time step, beta to the 0 will just be 0. We'll have u ct minus, and then lambda t times all this stuff, ct plus st minus 1 plus r t minus 1 st minus 1 minus yt. Okay, that's t equals 0. Plus, go to t equals 1. We'll have beta all times u of ct plus 1 minus lambda t plus 1 times, using as many brackets as I can here, ct plus 1 plus st plus 1 minus 1 plus rt. I'm just adding 1 to all the t's. Yeah, st minus y t plus 1, close squirrelies. And this was the t equals 0 chunk. Okay, so this part here, yeah, is t equals 0. This part here is t equals 1. So what's left? We have more sum. The sum that's left is the sum from t equals 2 to big T, beta to the t, mu of ct. Okay, so all I did was I broke the first 2 pieces off so that I could see that there's an st here and there's an st here. Yeah, here and here. That's why we get this term and this term. Do I need to break off the third part? No, I don't, because this st plus 1 will go to 0. This will become st plus 2 in the next part. This will be st plus 1. That will be 0. That's 0 derivative with respect to st. Okay, so all you need to do is look in the first 2 bits in this particular problem. Okay, and that's how I get these 2 expressions. Of course, I could solve for lambda t. And before I do, I mean, where are we going? We're getting the consumption-Euler equation. So you should pause the video and solve for the consumption-Euler equation. Unpause, come back and have a look. Okay, so you solved. We can get, how do you do it? You solve for lambda t first. You get lambda t is equal to the first derivative of utility with respect to consumption, mu prime ct. And that's going to be true for all times, yeah? So we can also know that lambda t plus 1 is equal to mu prime of ct plus 1. Okay? Why is that helpful? Because when we come down to this equation, we're going to plug in this and this. So solving this equation first, we can come up with lambda t equals beta 1 plus rt lambda t plus 1. And then we substitute for ct. So we get mu prime of ct is equal to beta 1 plus rt mu prime of ct plus 1. And that's the consumption-Euler equation. Of course, you could restructure this equation a little bit, right? Put the beta mu prime ct plus 1 on the bottom. Yeah, we're kind of used to seeing it that way. But this is the Euler equation. And the last thing we'll do in this video is look at a simplification that will give us some insight into this notion of consumption smoothing. So let me clear the screen and let me write down our Euler equation again. So the Euler equation, was given as mu prime of ct equals beta 1 plus rt mu prime of ct plus 1. Yeah. Now let's assume, with no evidence, but just assume for fun, assume that RT never changes. So we have a fixed interest rate. RT equals R for all t in the sequence of t's, which is 0 until capital T. Okay? And furthermore, assume that beta is equal to 1 over 1 plus R, which we know is like the steady state value the steady state value. We saw in TD, you can derive this or motivate this by a steady state argument. We saw it in the RBC, we saw it in the permanent income model. Okay, and then plug in these assumptions to the Euler equation. Okay. Go ahead and do that, pause the video, and have a try. And what do you come up with? Hopefully you see quite quickly that if we plug this in, beta will become 1 over 1 plus R. 1 plus RT will become 1 plus R, mu prime of CT. Okay, and this just cancels. So we get that mu prime of CT is equal to mu prime of CT plus 1. So under these simple assumptions, we get that the derivative of utility with respect to consumption today is equal to the derivative of utility with respect to consumption tomorrow. Is this a valuable thing to know? It is. We can say something about CT and CT plus 1 if we say assume mu prime is invertible. Okay, so assume mu prime is an invertible function. What do I mean by that? I mean, we can find there exists a function exists a function g of x such that g of mu prime of x equals x. Okay? Yeah, so examples would be like the x squared and square root of x. Yeah? So if I go square root of x squared, I get back x. Assume x is positive, okay? Or log and exp. Yeah? So assume that g has some kind of inverse function, or mu prime has some kind of inverse function so that I can flip it around, and then apply the inverse to both sides. So we are going to go g of mu prime of CT on the left, and that's equal to g of mu prime of CT plus 1 on the right. And we know that this is equal to CT, and this is equal to CT plus 1. Okay? So what have we concluded by this? We conclude that the best consumption trajectory, optimum consumption trajectory, is constant. So what does that mean? It means that we want to choose our consumption plan. So remember, the problem is not to choose consumption today. The problem is we're standing at the beginning of our lives and we want to choose consumption forever. The best choice is the one where we choose a level of consumption such that we're eating the same amount every day. Yeah? I want to make sure that the amount that I consume today is going to be exactly the same as the amount that I consume when I'm 50, when I'm 80, when I'm 100. Yeah? And this is an extreme result. This is an extreme example. We can call this an extreme example of consumption smoothing. Consumption smoothing is this idea that we prefer trajectories that are smooth to trajectories that are not smooth. We prefer to live a life where all of our days are more similar. We don't want to live in boom-bust cycles. We don't want to live a life where we consume nothing while we're PhD students, and then we get jobs in hedge funds, and then we consume a lot. Yeah? If that's the life we're going to lead, the economic theory says that we should use debt. We should take on a bunch of debt while we're a PhD student. in anticipation of the fact that we're going to be a hedge fund manager later in our lives, and then sort of pay back the debt when we have money, and then live a little bit better when we don't have money. So we're going to use savings and debt to smooth differences in consumption over the course of our life. Okay, so this idea of consumption smoothing is very important, and we see that under the assumptions that we have a fixed interest rate and that beta is set such that the interest rate is equal to the steady state interest rate, we get perfect consumption smoothing forever. Oh, and also income is known. Okay, so this is kind of the first example. In the next video, we're going to push this model a little bit farther. We're not done with it yet, but this is a really good first result. In the next model, we're going to find our g function. Yeah, so how do we choose this c bar? C bar, what is c bar? C bar is that fixed level, yeah. So we can say that c bar is equal to ct is equal to ct plus 1. And that just comes from this equation. Okay, if ct is equal to ct plus 1, then we can say they're both equal to some constant c bar. So the question is, what is c bar? Okay, and we're going to answer that in the next video.